we made a list of all of the forces, and this is the page I meant to be on, talking to the wrong screen. So again, vectors is new. If we make a list of all of the forces we've encountered thus far in our physics career, there was, and just in no order, there was the normal force. Well, I'll just write down symbols. We all remember the normal force. We remember tension force. You remember the weight force, weight, Fg equals mass times gravity. You remember normal force. You remember kinetic friction, static friction, and the list goes on. You remember universal gravitation. So Fg generally is G m1 m2 over r12 squared. You remember the buoyant force. The buoyant force is rho Vg, and maybe some other things. You remember the spring force. So anyway, my point here is that you guys have worked with a whole lot of forces. And there's probably some other ones that I'm forgetting off the top of my head. This is a brand new force. This is going to be F underscore E for electrostatic. The electrostatic force between two charged objects is K Q1 Q2 over R squared. R12, the distance between 1 and 2 squared. So this is new. This is the heart of chapter 21. This is the basis, literally, of, I think, the next 5 chapters. There's going to be a lot of stuff we do beyond this, but I think you could argue that kind of everything starts here. So this is a short chapter as far as homework problems. So the homework for Sunday is very light because this is an exam week. So makes sense to have a lightish homework on Sunday, but it doesn't mean it's not that important, because this is a fundamental pillar of what's ahead of us. And because now we go from thermodynamics to electromagnetism. So I'm not going to go into really much more background, because the expectation is you have already achieved a lot of digestion with the chapter 21 lecture video. Again, the goal has to be, you should not allow yourself to step into a Zoom class on a Tuesday morning without having digested the associated lecture video. It's so much better. Again, no one's in trouble. I don't know what you're doing. I'm just saying, common sense says, your experience says it's going to be so much better if you've seen the lecture video ahead of time. So having said all of that, here's our first problem. We have 3 charged particles lying on an x-axis. 1 and 2 are fixed in place. 3 is free to move, but the net electrostatic force on it from particles 1 and 2 happens to be 0. The distance between 1 and 2 is the same as the distance between 2 and 3. This is our dollar sign. We're after this ratio. Okay, so here's my thing. Here's my approach. This is a force problem, which means, again, forces means vectors, and a vector means magnitude and direction. And we've seen a lot of this before with gravity. There's a lot of parallels between gravitational force and electrostatic force. The one big difference is with gravity is always attractive. So the gravitational force is always attractive. One object will always pull on another object. The difference here is with the electrostatic force, it could be attractive or repulsive. You've heard that expression, opposites attract, likes repel. So that's the big difference. And actually, the fact that it can be either does make it quite a bit more complicated. But it's not that much more complicated. So what to do? Number one, I'm going to say, well, if the force on 3 net, this is how I'll write it, subscript notation. If the net force on particle 3, so let me just talk about convention, a little sidebar here as far as, and I think we've been doing this, I just want to maybe stress this again. In terms of convention, here's the convention. Let's always endeavor to say it's F on what? F on what? From what? From what? Let's use that question or that convention. F on what? From what? So for example, here, well, I'll get into it. This means, so this means the F on what? This first subscript is on what? On particle 3. From what? Net. So this is the on what, from what convention. All right, so I know the net force on particle 3 is 0 based on the statement. So there's no net force. There's no net force acting on particle 3. That's good to know. And I know these particles are charged. So what the heck? I don't know what's positive. So you know what? I don't know what's positive, what's negative. I'm going to go out on a limb here, and I'm just going to say, you know what? If you're not going to tell me what's positive and what's negative, I'm going to go out on a limb and just say, I'm going to say this is positive. I'm going to say this is a positive charge. So this is just me saying that's a positive charge. If the net force on particle 3 due to particles 1 and 2 is 0, you know what that means? I must have a leftward oriented force. So let's draw that. I must have a force acting on particle 3 that's pulling it leftward. And you know what? I must have another force on particle 3 that's pushing it rightward. That has to be the case. Because once again, the problem says there's no net force acting on particle 3. And if all of these particles are charged, which they are, because it says so, it says if 3 charged particles, so I can't get out of this by saying, well, maybe there's no charge on these particles. I can't say that. So if particle 3 is positive, and this is just my stab at it, stab in the dark, then I know one thing must be true. I know that particle 2 must also be charged, but does particle 2 have to be positive and negative or negative? And the answer is, I don't know. So I'm going to go out on a limb again and just say, I'm going to call particle 2 positive. If particle 2 is positive, then I for sure can label this F on 3 from 2. Okay, that I can say with certainty, because if particle 2 and particle 3 are positive, there's a repulsive force. And that means, as long as I'm making things up, if I'm making up charge signs, polarity like this, then I have to call this negative. I have to call Q1 a negative charge, because that means particle 1 and particle 3. If particle 1 is negative, particle 3 is positive, it means that this is the direction of the force acting on particle 3 due to 1. So this would be F on 3. It's always the on what, from what, on 3 from 1. I know that has to be the direction of that force. Let me change this. And once again, this must be the force on 3 from 2. Okay, that has to be the case. And you could say, well, what if I made particle 3 negative? You could do that. You could leave particle 2 positive, or you could change particle 2 negative. But this is all I can do. I'm just using what I'm given, and I don't have any other specifications. So I am just going to proceed with these, again, these just labels, these conventions. Let's do so you know what that means. The sum of all forces acting on particle 3. I'm just going to do force analysis. I have negative F31. So the electrostatic attraction between 1 and 3 is pulling it to the left, hence the negative sign. And then I also have another force. This is called F32. The electrostatic force between particle 2 and particle 3 is repulsive. Thus, particle 2 is repelling particle 3, hence the rightward orientation of this force vector. Newton's second law says F equals ma. And I know one thing for sure. I know that A equals 0 if the net force equals 0. So just sort of stepping back a little bit in terms of force analysis if the net force equals 0. All right, so let's just keep going with this. And you could see this. I'm being maybe I'm definitely moving in teeny tiny baby steps, which is what I always like to do at first. So that means this. From step 2, I can see, aha, at the risk of overhyping the obvious, whatever the force is between 3 and 1, it's the same as the force between 3 and 2. So again, maybe you saw that minutes ago. You probably did. Let's apply Coulomb's law, which will be the first time we're applying Coulomb's law. This is Coulomb's law with subscripts. Here goes. F31 means K Q1. No, follow the subscripts. Let me back up one more step. Here, Coulomb's law is this. In general, as mentioned, well, here, this is Coulomb's law. So this is Coulomb's law. So I'll just reference that. Let's apply Coulomb's law and let's use subscripts. Okay, so step 6, F31, follow the subscripts. K Q3 Q1 over R31 squared equals K, follow the subscripts, Q3 Q2 over R32 squared. That's Coulomb's law. That's Coulomb's law plugged in for the force between particle 3 and 1 and the force between particle 3 and 2. I got to get, again, eye on the prize here. What is Q1 over Q2? So step 7, I'm going to get Q1 over Q2. So if I just do a little bit of rearranging for step 6, I can see, well, first of all, before I do anything else, let's go after the low-hanging fruit. K's cancel. And I guess that's it. So not that low, but the K's do cancel. The K is the Coulomb constant. It's a empirical constant. All right. So I want Q1 over Q. Oh, sorry. There is one more piece of low-hanging fruit. Q3. Okay. So it does get simpler. All right. So I want Q1 over Q2. That's my dollar sign. And from number 6, Q1 over Q2 is going to equal R31 squared over R32 squared. And R31 is the distance between 3 and 1. So the distance between 3 and 1 is, well, let me just do this the long way. The distance between 3 and 1 is going to be L12 plus L23. That's the distance between particle 1 and particle 3. It really is helpful to use subscripts like this, you guys, both in terms of keeping yourself organized and allowing me to follow your work easier. So the distance between 3 and 1 is this distance plus this distance, and I got to square it. And the distance between 3 and 2 is L23 squared. But once again, we know that L12 equals L23. So this boils down to Q1 over Q2 equals, and let's just call them all L. So this would be 2L squared over L squared equals 4. Okay. So that's the answer, but we have to be a little more careful. That's the magnitude. And I do know one thing, so I'll just keep going with notes here. Remember, weight. I know Q1 and Q2 must carry opposite charges based on the conversation or based on this visual. I know that whatever they are, no matter how you play this game, go ahead and make up different numbers, but however you play it, however you set this up, and you have a lot of leeway in terms of setting this up. I know particle 1 and particle 2 are oppositely charged. So whatever that ratio is, I could actually just do this. Well, number 10. So Q1, if Q1 is negative and Q2 is positive, then this is going to be, I'll just write like this, is less than 0. So therefore, Q1 over Q2 is equal -4. That's the ratio. You could say the magnitude of the ratio is 4, but I believe Wiley Plus wants you to carry along that sign. I think. Let me know if that's not right. But I believe they want us to carry along that, the fact that they're oppositely charged, and reflect that in that ratio. My tendency would just be to ask you for the ratio, but this is good. This is actually probably a better approach. Okay, so that's it. That's our first quiz. Pretty gentle, good way to get introduced with writing down Coulomb's law and vectors. Those are the two big takeaways. Hey, there's something called Coulomb's law, and vectors are a big deal again. So I'm going to get chapter 21, quiz 2 ready. Chapter 21, quiz 2. It's now 8:38. Okay, you should now see chapter 21, quiz 2. Let me know if you can't. This problem is going to highlight conservation of charge, which was its own separate section in the lecture video and on your green sheets. Conservation of charge. You've had other conservation laws before this one. You had conservation of energy, conservation of momentum, conservation of matter, conservation of angular momentum. So there have been some conservation laws in your past, and it's good. To me, it's good news to know you're working with a conservation law, because you just have to keep track of things. So this is an experiment. Let me read through it. In this figure, and let me just highlight key points. In this figure, 3 identical conducting spheres initially have the following characteristics. The charge on A is 4Q. And you could say, what does Q mean? Q in this case is just talking about the amount of charge. Amount of charge. And they're not, well, yeah, they're not really quantifying it. They're not throwing out any numbers. They're just giving a variable. So they're saying, whatever the charge is, let's just call it Q, or Q is the amount of charge. And for sphere A, they're saying sphere A has 4Q, whatever Q is. Sphere B is negatively charged, -7Q, and sphere C is neutral, no net charge whatsoever. Spheres A and B are fixed in place, so that's a keyword. They're not moving because it's like they're glued. They're glued to the table. They're not going to move even though there's forces acting on them. With a center-to-center separation that is much larger than the spheres, meaning they don't overlap. Okay, and now we do 2 experiments. So I'm gonna read through this experiment, and I'm gonna just sort of wing it as far as tabulating the results. So this probably isn't going to be the most efficient way to set up these experiments. 2 experiments are conducted. In experiment 1, sphere C is touched to A. So sphere C is made to touch sphere A, and then removed, and then it touches to sphere B, and then it's removed. So let's talk. So that's experiment number 1. Let me track that. So experiment number 1, and this is not going to be super elegant, but this is like, in many ways, this is a concept question. Most of this is a concept question. So this is how I would solve a concept question. I would just conjure up my own tables and my own, assisting visuals. So experiment number 1, I'm going to do, this is how I would do it if this were a concept question. There's sphere A, sphere B, and sphere C. And let's see, they start off with, sphere A starts off with a charge of 4Q. Sphere B starts off with a charge of negative 7Q. Sphere C starts off with no charge. And then maybe what I'm going to do here as well, and this is just me doing what I would do on a concept question, the total charge. The total charge right now is negative 3. Negative 3 is the total amount of charge between spheres A, B, and C. And then in experiment 1, sphere C is made to touch sphere A. So when sphere C touches sphere A, so I guess right now I'm going to look at these two. If sphere C touches sphere A, they're going to exchange charge. There's going to be a charge transfer, conductive charge transfer. So as soon as sphere C touches sphere A will give 2Q of its charge to C. Okay, and let's talk about that. Again, if sphere C, this is sitting here, sphere A is sitting there with a charge of 4Q. C has 0Q. If you contact sphere A with sphere C, you're going to have a charge transfer. You're basically going to, these charges here, you've heard the term likes repel. So this is a instance of likes repelling each other. These charges on sphere A do not like each other. They are all of the same kind. They're all positive charge. So I have a bunch of positive charges on sphere A. They're looking to escape as soon as possible. When sphere C comes into contact with sphere A, that's the opportunity for escape. When sphere C touches sphere A, you get this escape process where literally 2Q, half that charge goes from sphere A to sphere C. And you might say, why don't they all escape? Because again, the goal is likes repel. If I have sphere A will get rid of 2 of its 4Q. If it tried to get rid of any more, it wouldn't make sense, because then you'd actually have an excess. Then things would get overcrowded here, and you'd have, again, an imbalance. But right now, if sphere C touches sphere A, there will be a charge transfer and the charge transfer will continue until there's no more fertile ground to transfer into. Because from sphere A's point of view, sphere C is very fertile ground. Sphere C looks like the promised land. There's no crowding going on there. All that charge transfers to sphere C until there's no vacancy, until sphere C turns on, there's no vacancy sign. All right, so I think I've belabored that point enough. Sphere B is still sitting there at negative 7Q. Okay. So that's the change. I went from stage A or state A to state B. This is what's changed. My total charge is still negative 3Q. And that's good because charge must be conserved. So this is my sanity check. I need to always end up with a total charge of negative 3Q, because that's what I started out with. Okay, so in experiment 1, C is made to touch sphere A and then B, and then it's removed. So that's it. This is the end of experiment 1. Let us now begin experiment 2. I guess this is not the worst way to represent it. Experiment number 2, I have A, B, C, and total charge again. So let's do experiment 2. In experiment 2, starting with the same initial states. Okay, so here's my initial state. You know, it's a better way of writing this, I think. Instead of A and B, I like I for initial state and F, sort of in keeping with all the thermal stuff we've done. For experiment 2, it's the same initial state. So this is going to be 4Q. This is going to be negative 7Q. And this is going to be 0. Let's do the read through again. In experiment number 2, starting with the same initial states, yes. The initial state in experiment 2 is the same as the initial state in experiment number 1. The procedure is reversed. Sphere C is made to touch sphere B. So now I'm touching C to B. All right, so if I do that, I am now looking at B and C interacting. And as soon as they interact, this is what happens. Sphere C, again, has a giant no vacancy. I'm sorry. Sphere C has a giant vacancy sign. So sphere C looks like, again, ripe for occupation. So when C and B touch, I'm going to have some charge transfer to sphere C because, again, sphere C has a big flashing vacancy sign flashing on and off. And sphere C is willing to take half of B's charge, because if it takes any more than half, it wouldn't make sense. B fills up sphere C and it can't go past the full point. Otherwise, sphere C would have an excess amount of charge compared to B, and that wouldn't happen naturally. All right, so and let me do this negative. Okay, so that's what happens when B and C touch. Nothing happened to A. The total charge here, well, let's see. In the initial state, 4 minus 7 plus 0 is still negative 3Q. And I better have negative 3Q in the final state, which is here. I have 4, negative 3.5, negative 3.5. So that is still negative 3Q. So that's just a good sanity check. All right. So I'm done. I'm done with experiments 1 and 2. What is the ratio of the electrostatic force? So here's the dollar sign. What is the ratio of the net electrostatic force between A and B at the end of experiment 2 compared to that at the end of experiment number 1? So this is what they're asking in this question. They're saying, what is the ratio of the electrostatic force between A and B? So this is the electrostatic force between A and B at the end of experiment 2 to the electrostatic force between A and B at the end of experiment 1. Maybe I better do this. Experiment 1, number 1 and number 2. And that's the dollar sign. Let me read that again. What is the ratio of the electrostatic force between A and B at the end of 2 to that at the end of 1? Okay, so I think I'm writing that down the right way. So I basically have to look at, here's the end of experiment 2. Here's the end of experiment 1. All right, so let's just follow Coulomb's law. Number 1, number 2. What is in experiment number 2, at the end of experiment number 2, what is the electrostatic force between A and B? Well, here's A, here's B. Okay, so ready. The electrostatic force between A and B, I'll just write it like this, is K. Let me move over. Oop, 1 second. Okay, let me move this over. Number 2. or step 2. All right. The net electrostatic force between particle A and particle B at the end of experiment number 2 is K. I'm going to do it like this. It's going to be K QA over QB all over RAB squared. Just sticking with generic subscripts. Where RAB, this right here that I'm writing down, this is referring to the distance between A and B. Again, love those subscripts. The distance between A and B is set to just D, because A and B are just stuck in place. But anyway, this is Coulomb's law, because Coulomb's law is, generically speaking, K Q1, Q2 over the distance between 1 and 2 squared. So I'm just using different subscripts. So this is my numerator. This is my numerator. Here's my denominator. My denominator is the charge between A and B at the end of experiment 1. Here's the end of experiment number 1. Here's particle A's charge and particle B's charge. So let's just keep things. Let me do this. Because otherwise I'm going to start stepping on subscripts. Before I go to the denominator, let's just plug in numbers here. Before I go to the denominator, let's just stick with the numerator. So this equals K times QA. And again, I'm still looking at the end of experiment 2. So I'm back to here. So I just backtracked one step. So K QA, here's QA. QA at the end of experiment number 2 is 4Q. QB at the end of experiment number 2 is negative 3.5 Q. What is the distance between A and B? It's D. So this is going to be D squared. Okay. That's my answer. That's my, well, I'm just going to write it like this. It's going to be negative K Q, pull out common factor, negative KQ squared times 4 times negative 3.5 is something. 4 times negative 3.5 is negative 14. Okay, times 14. All over D squared. Okay, so that's my numerator. This is the force. This is the force, the electrostatic force between particle A and particle B at the end of experiment number 2. And I guess that's good. KQ squared over D squared. So let's do the same thing. Let me insert 1A here. At end of experiment number 2. Okay, so step 3, at the end of experiment number 1, this is what's going on at the end of experiment number 1. It's going to be, at the end of experiment number 1, I'm looking at again here, it's going to be K times QA, QB, again with just the generic starting point, all over RAB squared equals K times QA. This is going, here's QA. QA is 2Q. So I'm just making sure I'm mapping things correctly. This is QA times QB. QB is negative 7Q because of my table. So I'm leaning heavily on my table. There's QB, this is QB, all over the distance between A and B, which is still that same D. So the distance between A and B is D, and I square it, and that's the answer. So this equals negative KQ squared times, and I made a mistake somewhere.
I think
No, I don't think I made a mistake. Did I? Or did I?
you're supposed to touch B. It says to touch A and then to B. It says, so you forgot one step prior. I
Let's,
think.
let
It
me
says
see.
to touch C to A, then touch C to B
14.
after.
Experiment number 2 is in my 3.5. 4 times negative 3.5. Okay, so let me go through it again. 2 experiments are conducted. In experiment 1, let me go to my initial case. So just sanity check here. I'm starting off with AF4Q. So I'm starting off with 4Q for A, negative 7Q for B, and 0 for C. In experiment number 1, C is touched to A. So as soon as C touches A goes to 2Q, C goes to 2Q. Oh, and then you're right. And then separately to B. All right. So, geez, that's a mistake. Let me do this then. You're right. Okay, so let me move all of this down. Okay, and maybe get rid of it. All right, so this is I'm going to go back to just state A, from A to state B, and then state C, because I just didn't read that second clause or that next clause. In experiment 1, C is touched to A and then to B, and then all right. C is touched to A and then to B. Okay, so then when C and B are touched, so then A remains 2Q. And now this is going to be what? This would be negative 5. So this is negative 2.5Q and negative 2.5Q. And let's talk about this and sanity check it. My total amount of charge here is 2 minus 2.5 minus 2.5 is negative 3Q. All right, so this is my repaired. This is my error corrected, thanks to Jordan. This is my error corrected experiment number 1. And let me get rid of some of this scratch here. All right. That's updated. And not just because I'm paranoid, I'm going to read through it. A and B are touched, 2 experiments. A and C are touched. Got it. And then B and C are touched. Okay. I'm good with this. So you guys keep your eye on me. Obviously, I can't be trusted. So if we do this together, we can catch the mistakes on the fly. All right. Let's do experiment number 2. Let's do experiment number 2. The same initial state.
Professor, how did you go from negative 7 to negative 2.5?
Yeah, let's talk about that. All right, so you're good with B. So let me know if I need to talk about how I went from A to B, because that's what we're talking about. But when I touch, at this point, when I touch particles B and C right here, at this point, let me reuse this. When I go from A to B, this is what I have. I have C has a charge of 2Q. A has a charge of 4Q. B has a charge of negative 7Q. This is what happens when I go from A to B. A is 4Q, B is negative 7Q, and C is 2Q. So then the next part of experiment 1 was touching C and B together. So now these two are brought together. C and B are brought into contact with each other. So what these charges are going to do, again, these charges want to go to equilibrium as much as possible. If I have negative 7Q on charge B and 2Q on C, then if they're brought into contact with each other, they're basically going to reorganize themselves to be as spread out as much as possible, because like charges repel. So I have all of these like charges on charge C. I have all of these like charges on charge B. So they're going to do their best to get away from all of the other like charges because they don't like each other. So I guess how would that charge transfer happen between B and C right here? If I keep my eye on B and C because A is no longer part of the experiment, I have a total of minus 5Q. All right. So what kind of distribution will happen if particle B and C between them have a total charge of negative 5Q and they're brought into contact? If they're brought into contact, you're going to have, of this total negative 5Q of charge, you're going to have negative 2.5 of it will go to particle B, and then you'll have another negative 2.5Q of charge going to C. So if I have that, this is what happens after B and C are brought into contact with each other. This will go to negative 2.5Q, and this will go to negative 2.5Q as well. I think this is maybe the key step, the fact that between B and C, there is a grand total of negative 5Q of charge. And if you give them an opportunity, if you bring B and C into contact, if you give them that opening, that chance to relocate, they're going to relocate as optimally as possible to minimize the amount of repulsion. So does that make sense? That's a lot of explanation, but that's how, this is my thought process. And this is what's going on when you bring charges into contact. When you bring two charges into physical contact with each other, you will have charge movement to the point where everything is spread out even Steven. Okay. So that is a key point to talk about. An A, B, C total charge. So let's assume, and you guys can tell me if I'm wrong, I'm assuming I executed experiment 1 correctly. Here's experiment number 2. It's the same initial conditions. So I have 4Q on A, negative 7Q on B, and 0 on C. And then I'm going to read carefully. In experiment number 2, it's the same initial conditions. The procedure is reversed. C is touched to B. So if C and B are brought into contact, again, I'm looking at bringing C and B into contact. A remains unchanged. So A is still 4Q. That's not part of the process. That's not part of the activity. But as soon as C and B are in contact, this becomes negative 3.5Q, and this becomes negative 3.5Q. For the same reason, if C and B are brought into contact, then those charges have an opportunity to shuffle around and relocate, so you have the least amount of repulsion possible. Okay. So the procedure is reversed. C is touched to B and then to A. So, okay. So now we're going to look at C and A coming into contact with each other, which means B does not change. B is still negative 3.5Q. And then here's the question. What do I write down for A? After A and C are brought into physical contact, what goes in these boxes? Any shout outs? What goes in there and what goes in here? If now charge A has 4Q worth of charge and charge C has negative 3.5. Oh, and before I do that, let me do my running my total charge here. This better be -3. It is. And then state B here, step B, this better be -3, and it is, because 4 minus 3.5 minus 3.5 is -3. Okay, so if I play the same game and I bring A and C into contact with each other, well, let's see here. I have -4Q on A. I'm sorry, I have 4Q on A and -3.5Q on C. So between A and C, here's the total charge. I have 4Q minus 3.5Q equals 0.5Q. Okay. So what's going to happen? 4Q and -3.5Q, I have a total charge of positive 0.5Q, and that's going to be split in half. So this will become 0.25Q, and this will become 0.25Q. And if 0.25Q minus 3.5Q plus 0.25Q is -3Q. Okay. So in conclusion, if I did this experiment right, because I definitely did not do it right initially, but if I'm doing it right now, you guys go ahead and sanity check me. So your job, please, is to correct my mistakes and to ask clarifying questions or to ask for clarification. All right, so now I'm going to go back to taking the ratio. What is the ratio of the charge, the electrostatic charge between A and B at the end of experiment number 2 to the electrostatic charge between A and B at the end of experiment number 1? And maybe I'll fast track this a little bit. This is going to be K, QA, and QA is right here at the end of experiment number 2. Here's QA right here. So QA is a 4Q. I'm sorry, it's right here. So I caught my own mistake. At the end of experiment number 2, this is the charge on A right here. And so there's QA. So write that down. That's the charge on A, 0.25Q. What's the charge on B? -3.5Q. All over the distance between A and B, which is that's still unchanged. That's just going to be D squared. All right, so that's my numerator. That's my numerator, and I just want to sanity check myself. At the end of experiment number 2, this is QA, got it. This is QB, -3.5Q, got it. And the distance between A and B. All right, so I'm satisfied with my numerator. Here's the denominator. Denominator is the charge between A and B at the end of experiment 1. So that's going to be K times QA at the end of experiment number 1, which is right here. At the end of experiment number 1, A is 2Q. So let's write that down. 2Q times the charge on particle B at the end of experiment number 1, -2.5Q. -2.5Q. That's my all over D squared and done. And let me just sanity check. All right, so my denominator, this is the force between A and B at the end of experiment number 1. So it's KQA, got it, times QB. Okay, I think that's good. And then you can see everything cancels. K cancels, Q, 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 D squared, D squared. Everything cancels except for numbers, which is what you would hope to be the case. Okay. So in my case, when the smoke clears, I've got this ratio as 0.175. All right, so bit of a detour because of my lack of reading the question. But I will say one thing. This is how I would do a concept question like this. I would just scratch out tables like this. I would just make up my own tables, make up variables, so on and so forth. Didn't have to do a lot of that here, but while you guys are finishing up that, let me go to charge or quiz 3. Let's see, it's now 9:11. Let's do one more quiz and then we'll take a break because I think these are relatively, this would have been a pretty short problem, but I did make that mistake and I did want to talk about this stuff a lot, which I did. All right, so let me unleash quiz 3. Chapter 21, quiz 3. Nine 12. Okay. All right. As of now, I think you should see chapter 21, quiz 3. And it should look like this. Okay. And actually, we're going to use real charge values. In this figure, particle 1, Q1. So here's particle 1, here's particle 2. They're fixed in place. So they are glued. They're staple gunned in place. They're not going to move, even though they want to move, because they're going to feel forces. But they are fixed in place on an x-axis 20 centimeters apart. And so right away, I know that this is R12. The distance between 1 and 2 equals 0.2 meters. Particle 3, which is over here, particle 3, which is not shown, but it says particle 3, which we do know the charge of particle 3, is to be placed on the line between particles 1 and 2. So somewhere between particle 1 and 2, we have particle 3, which is maybe right here somewhere. Okay, so I'm going to label that particle 3. Particle 3 with a charge of Q3 equals 8e minus 19 coulombs is to be placed on the line between particles 1 and 2 so that they produce a net electrostatic force on it. In part B of the figure below, we are given the x component of that force versus the coordinate at which particle 3 is located. And then it's scaled. A, what's the sign of the charge Q1? So let's see here. Q3, the charge of particle 3 is positive 8 coulombs. So Q3 has a charge of plus 8 times 10 to the minus 19th coulombs. Coulomb is the unit for charge, just like kilogram is a unit for mass. Okay, so that's the charge on Q3. And I got to start looking at the graph here. We have a graph, And the question is, what's the sign of Q1 and the ratio of Q2 over Q1? Well, if Q3 has a charge of positive, Q3 has a positive charge, what's the charge on Q1 and what's the ratio? So I'm going to just start in on doing force analysis. This is a force analysis chapter. So step one, let's just do free body diagram. Free body diagram. All right. So free body diagram, I have the charge, free body diagram. So we're going to look at the charge on 3 from 1, and we're going to also look at the force on 3 from 1 and the force on 3 from 2. All right, so in the figure, particle 1 and particle 2 each have a charge of, or fixed in place, I should say. This is Q1. Let me just keep labeling things. So this is Q1. This is Q2. This is Q3. Okay. And we have a graph. So one of the things I can't help but notice from the graph is this point right here. This point right there. And at that point, number 2, at x equals 1, 2, 3. So at x equals, I guess you could say 0.25 or maybe 1/4. At x equals 1/4 of xs, the net charge on particle 3 equals 0. So this is again from the graph. From graph. Okay, so let's talk about that. Right here at this specific point that I'm highlighting in green, there is no net charge on particle 3. And let's just make sure I'm looking at this graph the right way. In the figure, the figure below gives the x component of that force versus the coordinate x at which particle 3 is located. All right. So that's it. So I'll add this. When particle 3, let me just keep going. When Q3 is at x equals xs over 4, that scaling factor, Q3 net equals 0, or F3 net. F3 net equals 0. Good. So step 3 is just a refinement of step 2. All right, so let's go with that. At this moment, at this point, I better do some free body diagrams. At this point, I have my force vectors. Let's look at if x is, let's just maybe can answer part A right now. If x is less than xs over 4. So in other words, if particle 3 is moving closer to particle 1, so particle 3 moves closer to particle 1. Let me just draw that right here. So let's just say if particle 3 moves to particle 1, it's a little bit too big. You can see from the graph, the graph shows a very positive force, very exponentially growing positive force. So this right here is showing a rapidly increasing net force on particle 3. That's what happens when I bring particle 3 near particle 1. Okay. So at that point, what is the charge on particle one? What does the charge on particle one need to be if, as I bring particle three closer to particle one, the net force on particle three is getting super duper positive? And that must be because particle one is a positive charge. So maybe I'll make a note. Let me make a side note about that, which is the answer to part A. So I'm just going to do over here. This is part A. And let me just sort of comment on what I just said. From the graph, as Q3, as particle 3 approaches particle 1, the net force on 3 gets really large and positive. All right, so that's my rationale. So the only way the net force on particle 3 can get really large and really positive as Q3 approaches Q1 is if Q1 is positive. So therefore, Q1 must be a positive charge because likes repel. And if Q1 and Q3 are both positive, you're going to get that repulsive force pushing Q3 rightward. Okay, so now that we know the charge of Q1 is positive, we can move on to part B. So this was maybe part B. And I'm saying at F equals, when Q3 is located right here, when Q3 is located at that quarter distance, which is right here, when Q3 is located precisely at this point, there is no net charge. So to continue, at this point, F31 must equal F32. And then as long as I'm talking about vectors, and as long as now that I know the charge on particle 1 is positive, this is my rightward facing vector, and this would be my leftward facing vector. And I know for a fact I can label this F on 3 from 2, and I know for a fact that I can label this F on 3, F on 3 from 1, because 1 is positive. All right. And if they're at this magic point right here, at this point, they are perfectly offsetting each other. So let's just go to Coulomb's law. F31, follow the subscripts. KQ1, I'm sorry, follow the subscripts. KQ3, Q1 all over R31 squared must equal F32. Here's F32, K Q3, Q2, following those subscripts, all over the distance between 3 and 2 squared. And before we go on, we can deal with low-hanging fruit. K's cancel, Q3's cancel, and things are looking easier. What's the ratio of Q2 over Q1? So let's develop this one more step because I think we're close. Step number 6. So I'm just going to keep going with step number 5. Here's Q1, the left side of the equal sign. What's the distance between 3 and 1? This is where I better update my drawing. I know this distance. I better start dimensioning things here. I know the distance between 1 and 2. Let me just clear the decks a bit, since all of that has been handled. Okay, this distance, charge 1 and charge 2 are 20 centimeters apart. So this distance right here is 0.2 meters. And as mentioned, that is R12. Okay. Particle 3 is located at this distance right here. This distance right here at this moment is XS over 4. XS for my number is 20 centimeters. So XS over 4 equals 0.2 meters all over 4, or 0.05 meters. That's the distance between particle 3 and particle 1. Okay, so with that in mind, I can go back to number 6 here. My left side is Q1, so Q1 is right here. What's the distance between 3 and 1? The distance between 3 and 1 at this moment, at this point, is 0.05 squared. That's the left side of my equal sign. The right side of my equal sign is Q2 all over R3, 2. What's the distance between 3 and 2? This is particle 3. This is particle 2. And the distance between 3 and 2 is going to be 0.15. 0.15 meters squared. 0.15 meters squared. Let me fix this. Okay. There. So then I guess we're done. You can solve for Q2 over Q1. Here's a question. Well, here's a point. Careful. What's the sign of Q2? What's the sign of Q2? What's the polarity of Q2? We know the polarity of Q1 is positive because that was given. Or no, we figured that out. We figured Q1 is positive. Q3 is a positive. Is Q2 positive or negative? So that's it. So I have right now more charged particles. So this is definitely bare bones basic stuff. And this is where we have to start to everything gets built up from here. So instead of having just single point charges, we have more complicated objects. We are definitely going to graduate from single point charges to more complicated geometries. But this is where we are establishing the foundations. Let's do the very careful read through here. We have a graph. Particles 1 and 2. Particles 1 and 2 are, again, fixed in place. So 1 and 2 are fixed in place. Got it. 1 and 2 fixed in place, meaning they're not moving. Particle 1 has a charge of 11e. So now this is my opportunity to talk about 11e. What does E mean? This is from the green sheet. So I'm going to go through this not incredibly slowly because you have seen E in the chapter 21 lecture video and it's on your green sheets. But just a brief recap. E has a name. It's called the fundamental charge. Fundamental charge, not to be confused with natural log base C, but E is the fundamental charge, and it has a numerical value 1.602 times 10 to the minus 19th coulombs. And what has a fundamental charge? And here's some fundamental charges. Well, let's write the words. An electron is fundamentally charged. A proton, a beta particle, which is a subatomic particle, a positron, which is another subatomic particles, and the list goes on. There's a number of particles in nature, in our universe, that all have a charge of E, fundamental charge. In the case of an electron, it's negative fundamental charge, or negative 1.602 times 10 to the minus 19th coulombs. In the case of a proton, it's not negative E, it's positive E, which means the charge on a proton is positive E, or positive 1.602 times 10 to the minus 19th coulombs. A beta particle has a charge of negative E. A positron has a charge of positive E. So that's what E is. This is, again, my chance to formally introduce in Zoom class, because again, you've seen it in the video, what this E is referring to. This is natural log base E. Okay, so back to the problem at hand. Particle 1 has a charge of 11E, and I don't know if that's positive or negative. So I'm just going to write down 11E, not knowing, I guess since I don't know if it's positive or negative, I'm just going to write down this is positive or negative 11E. So it's as if you took 11 electrons and just clustered them together, or 11 protons and clustered them together to comprise particle 1. All right. Particle 3 of charge Q3 is positive 11E. So we can say that with certainty. Particle 3 has a charge of positive 11 fundamental charge units. 11E is 11 fundamental charge units. And I understand how this could get kind of confusing, because here I am, I'm writing 1.602 times 10 to the minus 19th. And now I'm also saying, well, 11E equals 11 times 10 to the minus 19th coulombs. And let's not forget there's natural log base E. So anyway, it can get confusing, but I guess context means everything. Particle 3 has a charge of Q3. Particle 3 has a charge of Q3 is a positive 11E, is initially on the x-axis near particle 2. Then particle 3 is moved around. So particle 3 is movable. And particle 3 is movable in the positive direction of the x-axis. So particle 3 can move like this. Okay. Particle 3 is gradually moved in the positive direction of the x-axis. As a result, the magnitude of the net electrostatic force on particle 2 due to 1 and 3 changes. Figure B gives the graph of what's happening. Figure B gives the graph of the net force, the x component of that net force as a function of the position of particle 3. So this, again, I'm going to have to write this down. This is a graph of F, the force acting on particle 2 net. I need to just double check that. This is saying, as a result, okay, Q3 is moving the positive X direction. As a result of Q3 moving in the positive direction, the magnitude of the net electrostatic force on particle 2 due to particles 1 and 3 changes. Figure B gives the graph of that net force. Okay, just wanted to double check, because I'm telling you, if you're anything like me, you need to read a question 5 times before it kind of starts to make sense. And then every time, for the first 3 times I read it, I've misread it somehow. So it's the whole process. All right, so and then we have an asymptote. Let's draw. We have when you look at graphs, here's the list of things that you should look at when you graphical analysis. When you analyze a graph, you're just instinctively looking at x-intercepts. You're looking at y-intercepts. You're looking at crispy intersection points, intersections, just write it like that. Crispy intersections. You're looking at area under graph as in integrals. You're looking at slope. You're looking at inflection points. You're looking at max and mins, maximas, and minimas. And on it, so you might be to this point now, but when you're given a graph, you guys, it should just trigger a chain reaction of stuff to look for. So knowing, having worked with graphs enough, you kind of at this point, you can see, well, this seems to be kind of an interesting point. That point, that's a crispy intersection point. That is an X intersection point. So that point is of interest. And then it actually says in the problem statement, the plot has an asymptote. The plot has an asymptote that is given to us. So this graph asymptotically approaches that value as X goes to infinity. So let's draw that asymptote like this, and then maybe just position it. Okay, so I'm going to just say that's my asymptote, and I'll just write this down is this is F2 net equals 1.658 times 10 to the minus 25th newtons. So that's another key point you pick off from the graph. So I have two key points. I have the asymptote, which is right here, and I have this crispy intersection at y equals 0. This is my X intersection. X intersection happens at y equals 0. So let's go with this. As a multiple of E, and including the sign, good heavens, seems complicated, but we'll find out. What is the charge as a multiple of E and including the sign? What is the charge Q2? All right, so let's just jump into it. Let's look at that x-intercept. Let's look at x-intercept point. So I'm going to just say at that intercept point, the net charge on particle 2 equals 0. So then, that makes me think, aha, I know F2 net equals the force on 2 from 1 vectorially plus the force on 2 from 3. All right. So let's see, particle 3 has a charge of Q3 positive. Particle 3 is for sure a positive charge. This is, I wrote it down already. That's positive 11. So what happens at this point, what happens when particle 2 is at the origin, particle 3 is to the left, and particle 1 is to the left, and particle 3 is at equals 0 when x equals xs over 2. Okay. So let's talk about that. There is no net force. There's no net force on particle 2 when the distance between particle 2 and particle 3, which is shown here. This is the distance between particle 2 and particle 3. So this is R2, 3. The distance between 2 and 3. I guess let's just call that X. All right, so when particle 3 is at this location right here, this is particle 3 location. This is referring to this is the Q3 location. When particle 3 is located precisely at that point, there is no net charge on particle 2. What is that point? It's 1, 2, 3, 4 boxes. It's halfway. It's halfway to X sub S. So that's why I'm saying when particle 3 is located at that distance, XS over 2. Here's XS, and right here, this is XS over 2, that location. So there is no net charge on particle 2 when particle 3 is at that location. So let's run with that and see what we can squeeze out of it before we do anything else. So, all right, here's the net force. Here's the net force. F21. Here's how I'm going to write F21. K, follow the subscripts, Q2, Q1 all over R21 squared plus K. Actually, I better do it like this. Let me back up just a bit. Before I do step number 4, let me do vector drawings. All right. So I have, here's particle 2, and apparently I have to have a force vector going to the right, and I have to have a force vector going to the left. That's the only way you're going to get a net charge of 0. I mean, a net force of 0. All right. So what should I label? What should I label that force on the right? This is the F. This is the charge on 2. Is this from 3? What is this? Let's see. We have to brainstorm. Is this purple vector F23 or is it F21? And so I guess we have to ponder. Let's see. As Q3 goes off to infinity, the net force the net force on particle 2 becomes settles down to 1.658 E minus 25 newtons. So that means Q1 must be positive. And let me go through that again. As Q3, because this graph is showing what's happening as a function of Q3's position. So let me make sure I have this right. As Q3 moves off to infinity, here's Q3 moving off to infinity, the net charge on particle 2 is shown to be, from the graph, 1.658 E minus 25 newtons. Therefore, Q1 has to be positive. Q1 is positive. And why is that? Because if Q3 is off at infinity, basically Q3's influence is no longer felt. If Q3 goes off to infinity, Q3 has no real effect on Q2. So the only effect that Q2 feels is from Q1. And if the graph is showing, hey, it's a positive force, meaning the positive X direction, that can only happen if Q1 is positive. So then I'm going to just say, aha, based on all this conversation, Q1 is plus 11 E. I know that from the graph and this conversation I'm having in my head here. So Q3 is positive, which means Q1 is positive, which means Q2 must be negative. So, okay, and that's part of the answer. The charge on Q2 must be, Q3 must be positive. Okay, so this must be positive. All right. And that's right. All right. Q3 11E. Yes, that's right. Okay, just stuttering a bit here. Just double checking it internally. All right. So for sure, if Q1 is positive, this is the net force on 2 due to 1, correct? This is the net force on 2 due to 3. So fully labeled here, which means I need to update this expression. F21 is going in the positive direction, but F23 is going in the negative direction. So let me update that. Good. So finally, we know, and we knew this all along, but the force acting on 2 due to particle 1 is the same as the force acting on 2 from particle 3. So if we do Coulomb's law, follow the subscripts, this is going to be K Q1, I'm sorry, Q2, K Q2, Q1, follow the subscripts all over R21 squared equals F23. Here's F23, K2, Q2, Q3 all over R23 squared. Sanity check. This is the Coulomb force. This is the electrostatic force acting on particle 2 due to particle 1, and that's what this is representing. And this is the Coulomb force, the electrostatic force acting on particle 2 due to particle 3, and that's what this is representing. And I'm just trying to stay dedicated to subscripts. Number 5. All right, number 5. We're looking for what is the charge on Q2. Q2 is a dollar sign. So before we isolate Q2, let's take care of low-hanging fruit. K's cancel, K's cancel. Q2's cancel, Q2 cancels. So there goes my Q2, but you know what? I'm not going to completely despair quite yet. I'm just going to keep hammering on this. So because K and Q2 both cancel, I'm left with this. I'm left with Q1 over R21 squared equals Q3 over R23 squared. So I'm going to write what happened. What happened to Q2? Well, it canceled. I can't solve for Q2. But I'm going to keep this around just in case. What happened to Q2? The answer is I don't know. So look for another. Let's look for another relationship. Let's do some relationship building. Let's look for another relationship. And you know, one thing that comes to mind, look at what's going on. Look at Q3 as Q3 goes to infinity. Let's look at the case when Q3 is at infinity. Q3 is infinitely far away. If that's the case, I have this. I'm going to say negative F23 minus, that is minus, plus F21. So I'm going back to my vector diagram. I have F23 pointing in the negative direction because particle 2 is going to be repelling. I should say particle 3 is going to be repelling particle 2. That's why that's negatively oriented. And particle 1 is also going to be repelling particle 2. That's why that's oriented in the right direction. But at this case, when Q3 is at infinity, here's the net charge. It's not equal to 0. It equals F2 net. I'll just write it like that. And instead of F2 net equaling 0, like it did right here, F2 net now equals 1.658 E minus 25 times 10 to the minus 25th newtons. All right, so let's keep going with this. Number 9. Here's F23, negative K Q2, Q3 all over R23 squared plus F21, the Coulomb force, the electrostatic force acting on particle 2 due to particle 1 all over their distance squared. And I do have a number on that. It's 1.658 E minus 25 newtons. Okay. So I think I can get Q2 out of this. Let's keep going and get Q2 out of all of this. Well, first of all, maybe there is some low-hanging fruit here. What's the distance when I'm looking at Q3? If I'm going to look at Q3 off at infinity, what's going on when Q3 is off at infinity? I know this number. This number is pretty darn big. So R23, when Q3 goes off to infinity, this denominator becomes infinity squared. So this whole term right now goes to 0 because I have some numerator over infinity squared. So this whole thing goes to 0. So that's some low-hanging fruit. So you know what I'm left with in step 10? I'm left with, I'm going to isolate Q2. Q2 equals 1.658 E minus 25 newtons times R21 squared, R21 squared, all over KQ1. And here's K. Here's the first time I'm going to write. K is the Coulomb's constant. Here's K, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times, and also the denominator is Q1. Do I have a value on Q1? I do. Particle 1, and I know that's 11. So this is 11E. And let me sanity check all of this now. First of all, yes, this term, I'm confident that this term can be ignored. Because if Q3 is off at infinity, then there is no force exerted on particle 2 from particle 3. So yes, this is neglectable now. That goes to 0. I'm left with this expression. I want to isolate Q2. So let's make sure I did that without any mistakes. If I'm isolating Q2 in step 9 there, Q2 equals 1.658 E minus 25 times R21 squared, which I don't know, divided by K. This is the value of K divided by Q1. And again, I went through a whole segment of internal reflection where I figured out Q1 was positive. Right. And not only do I know it's positive, but the question statement told me it had a magnitude of 11 fundamental charge units. So I think that's good. So then I'm thinking, this is another moment. What's R21? What is the distance? What is the distance between particle 2 and particle 1? Question mark. What is that distance? And things were looking so good up until right now, because this was the initial setup we have. And the question statement said Q1 and Q2 are fixed in place. So that does ring a bell. These are fixed in place. But here's the question. I don't know what that distance is. So I'm just going to write down. This is R21 right here. This distance between Q1 and Q2, that's what I'm referring to as R21, and that's not given. So, but fortunately, I have step 5 that I think I might be able to draw on. All right, so then number 11. Back to step 5. Back to step number 5. Step number 5, I have R21 squared. R21 squared equals Q1 over Q3, Q1 over Q3 times R23 squared. Okay. You know what I better do? I better do, because this could be, I'm going to backspace over here. Do this. I'm going to call this 5A. 5A. And I'm doing that because the R23 in question 5 is different than the R23 in step 10. So 5A, I'm going to say the same thing. R21 squared equals Q1 over Q3 times R23 squared. Let's run with that. 5B. 5B says R21 squared equals Q1. The value of Q1 is 11E. The value of Q3 is also 11E. Is that right? Q1 and Q3. So Q1 and Q3 is just equal to 1. So R21 squared equals R23 squared. And in this, and when Q3 was located at that halfway point, so 5B, in 5B, Q3 is still at that excess over 2. R23, the distance between 2 and 3 was excess over 2. Excess over 2 squared equals excess. My XS is 1.4 meters. 1.4 meters all over 2 squared equals 0.7 meters squared. Okay. Equals 0.49. 0.49 meters squared. And let me just double check myself. Make sure I did, because that's a lot of operational stuff. Let me zoom out. Okay. All right. So I'm here in 5A. I went from 5. Here's 5. I'm feeling good about 5. Ended up, what happened to Q2? That was very disappointing. But now I'm back because I need to figure out what is the distance between particle 2 and particle 1. So from 5, I went from 5 to 5A. And if I rearrange statement 5 correctly, I would say R21 squared equals Q1 over Q3 times R23 squared. Okay. Which means R21 squared equals R23 squared. And R23, again, is the distance between particle 2 and particle 3. I'm highlighting that right here. So let me just add that as a note. When the net force on 2 was equaling 0, X, which is the location of particle 3, I'll just say Q3 location is at X equals XS over 2. It's right here. It's on the graph at this point. So I am very much focused on this particular point right there, that green dot. All right, so I think that's right. Particle 3 is at that location when there's no net force on particle 2. So having said that, XS over 2 squared, and for me, XS is given as 1.4 meters. So what's 1.4 over 2? It's 0.7 squared. Okay, so 0.49 squared is for me R21 squared. Okay, so there. Having said all of that, now we can let's update number 10. Update number 10. So I have Q2 equals 1.658 times 10 to the minus 25th newtons times R21 squared, which is 0.49 meters squared all over, dimensional analysis is probably a good idea here, all over 8.99 times 10 to the ninth newtons times meter squared over coulomb squared. This was a typo. This should have been coulomb squared. So, and just to reinforce this thing right here, this is K. That's the Coulomb constant. And then what else is in my denominator? 11E. And you know what I'm going to have to do? I'm going to have to convert this. So one fundamental charge unit, and I think Wiley Plus uses this conversion, 1.6 times 10 to the minus 19th coulombs. So let me convert 11E. So I'm going to get 11E times 1.6 times 10 to the minus 19th coulombs per E. That's the conversion. All right, believe it or not, that's my value of Q2, but we're not going to be done here. We have to convert again. So this is that E, this fundamental charge unit E cancels with this fundamental charge unit E. All right, so you know what I get? If I'm going to do dimensional analysis, which I really have to do, because you're going to do it on exam 1. Here's what I have from a dimensional analysis point of view. I have newtons times meters squared in my numerator. In my denominator, I have Newton meters squared all over Coulomb squared times coulombs. And you know what? That actually does spit out coulombs. So great success for those of you who are Borat fans. Great success. I do have coulombs that are resulting. So I feel good about the dimensional analysis. Now we just have to get a number on that. So calculator time, 1.658 E minus 25. Okay, store alpha A. Just doing it again. All right, I got the same number twice. I get Q2 equals 5.13 and some change times 10 to the minus 18th coulombs. I'm putting that in calculator memory location A, but that's not the answer because the question said you have to express this in terms of fundamental charge units. Okay, so I'll do that. So I'm taking my result for Q2, and then I'm going to convert. So I need to ask myself, I'm going to convert. I guess I'll do it like this. I have to convert from coulombs to fundamental charge units. So once again, here's that conversion factor times one fundamental charge unit over 1.6 times 10 to the minus 19th coulombs. So I'm going to take that answer and divide by 1.6 times 10 to the minus 19th. I need to divide it by 1.6 E minus 32. 32. So I think when the smoke settles, the value of my charge Q2 is 32 fundamental charge units. Okay. A lot going on in this problem. 32 E, fundamental charge units. That is the value of Q2. Okay. All right. It is now 10:15. We're actually doing pretty good on time, but we have one more quiz to do. One more quiz to do. Let me give me a minute to get it set up. Lots going on here. All right. Last question. Let me check the grade book. Let's just see how people are doing as far as completing all of these quizzes. Chapter 21 quizzes. Chapter 21. Quiz 4. I need to wait. I think there's still some. I'll wait for sure because there's a lot of people still working on quiz 4. And let me cross my fingers. You guys fight the good fight. If any of you basically just decided to look up the answer on Chegg or Course Hero, just Google the answer somehow. We all know these answers are easy to find. I'm hoping you didn't do that just because you've just hurt yourself. I mean, not really, but you've just lost the opportunity to struggle and get the wrong answer and troubleshoot. That's what you really lost, and that's very helpful. So keep working on this, and I'll get the next quiz set up. So stay away from trans fats, high carb foods, and Googling the answers. Not necessarily in that order. Chapter 21, quiz 5. All right, let me check on grades again. Better. Still quite a few people. Let's not hurry. Well, another few moments. Actually, let's do this. Let's resume at 10:28. So there it is. Now all of a sudden we have 2 dimensions. So we go from 1 dimension. Everything up to now has been 2 dimensions. Although I think there are some other 2-dimensional homework problems. And don't forget, let me just give another shameless plug for the deep dives, which you see here on the screen. And I think for chapter 21, there's quite a few deep dives. Well, I think some of these, let's see, but there's the deep dive repository. For chapter 21, there are 2 deep dives. So there are 7 homework problems. Of the 7 homework problems, 2 of them are deep dives. And of the 5 that aren't deep dives, we're doing all of them now. So that's what this is. Deep dives are there for the other ones. All right, so let me do some graph paper. And this is, so there are, I believe, other two-dimensional situations, but this is the first one we're doing here. All right, we have in this figure, what's the magnitude and direction of a fourth particle? What's the magnitude and direction of the net electrostatic force on particle 2 due to the other 3 particles? That's the question. So it's short and sweet. What's the net charge? So this is here's 3 particles. I have particles 1, 2, 3, and 4, as you see here. And I have this visual here because it's just easier to read. There's Q1, Q2, Q3, Q4. And the question is, here's the dollar sign. What is the net electrostatic force on particle 4 due to the other 3 particles? Okay, so let's see. Let's do the read through. All 4 particles are fixed in place, because if they weren't fixed in place, they would definitely move. So these are glued again to the tabletop or to the screen, and they can't move, even though that they're exerting that force. The forces they're feeling are not equal to 0. So they should move, but they can't move because they're fixed in place. Q1 is a negative charge. So I'm just going to say Q1 is a negative charge. So Q1 is down. This has a negative charge, negative. All right, got that. Q2 is a positive charge. So Q2 is positive. Q3 is a positive charge. Q4 is also a positive charge. All right, let me double check. Q1 is a negative charge. Did I get that right? Q1 is negatively charged. Yes. Q2 is positively charged. Yes. Q3 is positively charged. Yes. Q4 is positively charged. Yes. So now let's do free body diagram. Let's draw the forces acting on particle 4. That is, after all, what I'm after here. So I have, all right. So between 1 and 4, this is what's happening. There you go. Particle 1 will attract particle 4. Done. What about particle 2? Particle 2 will repel particle 4. How do I know that? Particle 2 is positive. Particle 4 is positive. There's mutual repulsion there. Okay. Particle 3 is positive. Particle 4 is positive. So we have mutual repulsion again. All right. And let me label all this stuff. Make sure, you guys, this is the fundamental setup. Make sure you're asking questions and you're pointing out mistakes, but I'm saying, okay, this is particle 1 is negative, particle 4 is positive. So that's mutual attraction. So this is F on 4 from 1. Particle 2 is positive. Particle 4 is positive. That's mutual repulsion. So this is F for 2. Particle 3 is positive. Particle 4 is positive. That's also mutual repulsion. So this is F for 3. All right, those are all of, and these are vectors. So draw them as vectors. And our job is to find the net force. Now, what you could do here, the net force on 4, this again is the dollar sign. There's a lot of simplifications we can make. This can collapse and simplify a lot because of symmetry and simplifications. I mean, notice that Q1 and Q2 have the same value, and both of them are half of Q3 and Q4. So anyway, I am not going to do any of that. I'm not going to take advantage of any simplifications or fast track approaches. I want to assume that there's nothing that we can do to simplify, at least at the very beginning. All right. So because if I gave you this what if I give you this problem on an exam and Q1 is just some weird random number and it's not it's not a multiple of Q2 and Q3. So what if I gave you 4 just randomly generated values for Q1, Q2, Q3, and Q4? What would you do then? So again, I don't want to take advantage of any sort of low-hanging fruit just yet. All right, so this is my force diagram. I'm going to do, here's what you should do. Anytime you have 2D vectors like this, let's always take the same approach. And this comes from the prior physics class. And if it doesn't, if this is your first time hearing it, this is a very logical approach. I'm going to call this angle. What is the angle that F41 is making? It's making this angle. So ready, set, go. All right, I'm going to label this green. I'm going to call this theta 41. And so here's my convention. This is what I'm sticking to. And this is enormously helpful. It's a bit time consuming to set up, but once you get it set up, it's way better. So let's express all angles as going counterclockwise with respect to plus x axis. Okay, so this is the approach I want to take. And it's really, I mean, this, if you're going to end up in science or engineering, you like best practices and you like rational methods and all of that stuff. So I'm going to express all angles as counterclockwise with respect to the positive x-axis, which is why I'm expressing theta 41 that way. Theta 41 is the angle made by F41. Similarly, here's angle theta 42. So I'll do, maybe I'll go way over here. So here's there. This, I'm going to call this theta 42, which is the angle made by F42 with respect, going counterclockwise with respect to the positive x-axis. So again, remember, this is the approach we're taking, just brutally rational, cold-heartedly rational. Theta 43 is right here. Okay, this is theta 43. It's the angle made by that force vector 43. So that's that. So let's just have a little sidebar here. Theta 41, for me, theta 41 is going to be 180 degrees plus theta 1. So for me, 180 degrees plus theta 1, 180 degrees plus theta 1, my theta 1 is 42. So and you do your angle, this is 222 degrees. Theta 42, let me make sure. So let me just go through this. This is theta 41. Theta 41 is right there. And yes, it's 180 plus theta 1. So I'm confident about theta 41. Theta 42 is 270. So I can see that right away. That's theta 42. Theta 43 is, let me just, theta 42. This is theta 42. It's 270. Here's theta 43. Theta 43 is 180. Okay, so again, all this setup is worth it, especially if we couldn't do some like no-brainer type of simplifications, which we can do here. All right, but I guess that's good. I want to get rid of this highlighter. Okay. All right. So now let's proceed. This is a job for an XY force table. So this is, again, this is just a nice rational way to tally up. So this is my organizational table. I'm going to make a table. This is going to be name, vector, And I would give all this stuff to you. I'd give this layout. You don't have to memorize this. I'd say, hey, use this table to calculate, to show your work. Use this table to develop your solution. Or I think I would say base your solution on this table that I'm throwing out here. Name vector X, Y. Okay, so let's go through it. Let's just go through. I have 3 force vectors. Here they are. Here are the 3 force vectors. I have F41. F41, which again is the electrostatic force acting on particle 4 due to particle 1. Let me just say that again. F41, which is right here. This is the electrostatic force acting on particle 4 from particle 1. Again, it's always F on what, from what. All right, so that vector looks like this. It's doing this. There's F41. And then here's the angle. Here's the angle that I'm associating with that. I'm going from, this is my plus x-axis, and this is theta 41. Theta 41. Okay. So now that the setup is happening, you guys know from your unit circle days, here's the unit circle. So just to digress just for a bit, unit circle is enormously helpful. But this is the unit circle, and you should remember that if you have this, a particle right here, or if that's your location, you should remember from your unit circle days that this coordinate right here, dot, 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 that coordinate, this x coordinate is brought to you by cosine of theta. You should remember that this y coordinate is brought to you by sine of theta, and this is angle theta, and this is this has a value of 1. That radius line has a value of 1. So again, unit circle is the gift that keeps on giving. I'm drawing it here again just to remind everyone that cosine is responsible for the x component and sine is responsible for the y component. So having said that, what is the x component of the force exerted on particle 1 due to particle 4? It's Coulomb's law. So let's just say it's going to be, follow the subscripts, K, following the subscripts, Q1, Q4, all over, oh, I didn't follow the subscripts. It's K, Q4, Q1, all over R41 squared times, and I got to capture the x component, cosine theta 41. That captures the x component. So this is why I like this setup so much, because it's basically just spending a lot of time setting up the problem, being very structured, very meticulous, and then repeat. So the y component is exactly the same as the x component, except this is going to be k. Let me get it better. It's exactly the same as the x component. Follow the subscripts. It's k q4 q1 all over r41 squared. But now I need to capture the y component. That is a job for sine theta 41. Sine captures the y component. And now we can cruise. Now this is F42. Let's take a look at the vector F42, which is the electrostatic force acting on particle 4, which is right here, due to particle 2, which is right here. Because they're both positively charged, F42 is pointing straight down. I know that's theta equals 270, and I know cosine of that is 0 and sine is -1, but that's what I'm saying. I'm going to drag this along, even though I could get rid of it right now. I'm not going to. So I'm going to draw a vector. This is F42. This is vector F42. And this is the angle going counterclockwise with respect to the positive x-axis. There it is. This is theta 42. And so my x component, follow the subscripts K, Q4, Q2, all over R42 squared. Cosine captures the x component, theta 42. And same for over the y component. This is going to be K, Q4, Q2, all over R42 squared sine of theta 42. All right, one more, and then we do some more crunching. This is still set up. F43. What is the electrostatic force acting on particle 4, which is right here for the umpteenth time, due to particle 3? Since they're both positively charged, that's F43 is in that negative x direction. So visually, it looks like this. Here's F43, F40. There's my F43 vector. And again, I'm specifying everything with respect to going counterclockwise with respect to the positive x-axis. So there. This is theta 43. Follow the subscripts K 43, Q4, KQ4, Q3 all over R43 squared times sine of theta 43. I'm sorry, cosine. Capture the x. Cosine of theta 43. Same for the y. K, Q4, Q3, all over R43. R43 is referring to the distance between 4 and 3 squared. Capture the sine, the y component, sine theta 43. And that's it. So we are officially done with the XY force table setup. This whole thing is known as an XY vector table is the better name, XY vector table. And this, again, I believe this is a very good approach. This is a very effective approach in terms of breaking things down and setting them up, because now all I have to do is add stuff up. Here's F4 net. Here's the dollar signs, F4 net. Okay. This is the dollar sign. I'll write it like this. F4 net X, that's a dollar sign, and F4 net Y is the other dollar sign. Okay, so let's just stick with the whole decomposition approach, because what I can see here, I can see that if I do this component plus this component plus this component equals this component. That's my X component. Similarly, for my Y component, I'm going to say the exact same thing. This component plus this Y component plus this Y component equals this Y component. So that's all I'm doing. And this is very meticulous, but when you think about it, it's probably good that we spend a lot of time doing really meticulous stuff. I mean, wouldn't seem right otherwise. Because again, science and engineering kind of means you are into being hyper meticulous, or the more hyper meticulous you are, the better. So let's just now crunch numbers and avoid getting rid of stuff that, for example, let me just point that out and then forget I ever said that. You know that this whole term here goes to 0. You know that this whole term here goes to 0. But let's pretend that that's not the case, but just saying. All right. So let's crunch numbers. Okay, I want to let me move some things out of the way. I'm going to move all of this stuff over here a bit. Okay. All right. So number one, let's add up all x components. So if I add up all x components, this is what I get. Brace yourself. I get k q4 q1 all over r41 squared cosine theta 41 plus k q4 q2 all over r42 squared cosine theta 42 plus k q4 q3 all over r43 squared cosine theta 43. And what does that equal? That's going to equal the net force acting on particle 4 in the x dimension. Now maybe we can do a little bit of low-hanging fruit. In this case, because theta 42 is 270, and I know the cosine of 270 equals 0, thanks to the unit circle. Okay, and your calculator. If you didn't know that from the unit circle, you know that from your calculator. So I'm just going to, I guess, start doing some simplification. Theta 42, this whole term equals 0. All right, so let's just do an update. And then the y component is going to go way faster. All right, so here we go. We're still on the x components. I have, all right, k, maybe I'm going to factor out a kq4. If I factor out a kq4, this is what I get. kq4, I'm pulling out a common factor from step 2. If I pull out that common factor, I have kq4, and then what's left behind? q1 cosine of theta 41 all over r41 squared plus q3 cosine of theta 43, which I know that equals -1, but that's fine, over r43 squared. That's it. This is my, well, I still have to process some more, but again, what am I doing? I am calculating the net force acting on particle 4 in the x direction with numbers. I think it's time to plug in numbers. So with numbers, let me move this over. Make that a little bit smaller. Okay, with numbers now, let's just keep going. Equals k is 8.99 times 10 to the 9th. I'm going to leave off the units just for space. You know by now, you have to do the dimensional analysis. So that's k. Here's q4. For me, q4 is 6.4 times 10 to the minus 19th coulombs. I probably will end up doing dimensional analysis on this, but as a follow-up. All right, so that's KQ4. So I just handled KQ4 right here. All right, so in parentheses now, I have parentheses Q1. For me, Q1. Now, careful. Q1 is -6.4 times 10 to the minus 19th, but I've already accounted for that negative. So this whole vector setup that I'm showing you here, that accounted for the positives and negatives. So it would be incorrect. I don't want to enter -6.4. I'm just going to enter 6.4 times 10 to the minus 19th times cosine of theta 41, which is 222 degrees, all over R41 squared. And that's given for me. R41 is this distance. What is the distance between particle 4? What is the distance between particle 4, which is right here, and particle 1? That's given as D1. D1, and I have a value for D1. For me, D1 is 0.047 meters. Okay, that's that. Plus, I'm running out of space here. I'm gonna move this whole thing down, I guess. So let me just stack that, keep going. I guess I'll call this step 4. So I just wrote down Q1 theta 41 times cosine Q1 times, all right. I'm going to double check this too. All right, plus Q3. Q3 is 12.8 times 10 to the minus 19th. 12.8 times 10 to the minus 19th coulombs. There's Q3 times cosine 4.3. Cosine of 4.3 is cosine of 180, which I know is -1, but it's fine. What's the distance between 4 and 3? According to my given graph, the distance between 4 and 3, let me show that here clearly. Here is 4, here is 3. That distance is D3. And for me, D3 is 0.027 because 2.7 meters, I'm sorry, 2.7 centimeters is 0.027 meters squared. And then close parenthesis. Now, I just want to sanity check this just because, again, minutiae. All right, so here's K. Got it. Here's Q4. Okay. This better be Q1. Q1 is 6.4 E minus 19. Cosine theta 41 means cosine of theta 41, which for me is 222. All over R41 squared. This is R41, the distance between 4 and 1, which is D1, which is given as 0.047 meters, plus Q3. Is this my Q3? Let me double check that. 12.8 E minus 19. Cosine of theta 43, which is 180. Yes. All over the distance between 4 and 3. The distance between 4 and 3 is D3, which is also 0.027, D3, 0.027. Okay. I think that's good. Let's get a calculator. Let's put that in your calculator and store it. And then the Y components will go a lot faster because we can kind of just copy and paste this approach. Okay. I get a number. I'm going to do this twice. This is so messy that I don't trust myself not to make a mistake. I'm going to get a number and put that in calculator memory location A. Times alpha A. I got the same number twice, which makes me feel confident. So right now I get, this is -1.13 and some change. times 10 to the minus 23rd. That is a small number. That's what I'm getting. I got that number. I'm putting it in calculator memory location A. This is courtesy of my X force column, my X column. I'm going to do the same thing here. Let me change markers a bit more than that. I'm going to do the same thing for Y, number 5. I'm going to go over here. Number 5. Add up all Y components. Add up all Y components, just like I did for X. And I'm going to do the same thing for Y. Okay, number 6, here goes. Okay, let me just brute force this through. And you can see it's not, I don't know, it's not taking that much time. But if I add up all of these Y components right here, all of these Y components, let me just do this the meticulous way. I've got K Q4, Q1 over R41. And I know what all this stuff is now. And this is sine. So not cosine, but sine. Sine of theta 41 plus K Q4. And when you do this, the one benefit about doing this horrendously meticulous process is it really does force you to double check everything. Like, for example, I forgot to square R41, but I did now. And this is R42 squared times sine of theta 42 plus K, follow the subscripts, Q4, Q3 all over R43. Now remember numerically what that is. So things are looking much more familiar. Sine of theta 43. And now we can do low-hanging fruit again, because I know that the sine of 180 is 0. So I know the sine of theta 43, this sine of theta 43 does in fact equal 0. You know that from the unit circle or from your calculator. So I'm not going to drag that along anymore. I think the point has been made. But if it wasn't equal to 180, then you would have to drag it along. So this whole thing equals 0. So let's go to the next step. Step 7. Here's my Y component. It's common factor. It's KQ4. This is going to look exactly like, well, not exactly like step 3. So let me not say that. But I'm pulling out a common factor, and I'm left with Q1 sine theta 41 all over R41 squared plus, and this is where it's a little bit different, plus Q4, I'm sorry, Q2 times sine theta 42 all over R42 squared. That's the answer. That's the answer right now to the Y force. This is the net Y force acting on particle 4. All right, so with numbers, step 7, step 8. So I'm just going to do again, F for net Y. So with numbers, it's going to be the same, largely 8.99 times 10 to the 9th Newton Coulomb squared per meter squared times Q4, and this again is going to help me sanity check. I think I know Q4 is in fact 6.4 E minus 19. Okay, and I'm looking at step 7, parenthesis, Q1 is, just to double check, Q1 is 6.4 E minus 19, 6.4 E minus 19. And it really is important to understand why I'm not including that negative sign. I'm not including that negative sign here in step 8 because I've already accounted for the fact that Q1 is negative and Q4 is positive. All right, so then to continue, times sine of theta 41, sine of theta 41, sine of 222 all over the distance between 1 and 4, and that's still the same. That's still D1. D1 is the distance between 1 and 4, and that is 0.047 meters squared. Okay, plus Q2. Q2 for me is 6.4 times 10 to the minus 19th times sine theta 42. Sine of theta 42. Theta 42 is 270. So yes, I know that's equal to -1. All over R42. What's the difference between 2 and 4? According to that graph, that's D2, and D2 is 0.027. 0.027 squared. And then just because this is so horrendous, I got to double check. All right. This is, so I'm looking at step number 7. Here's KQ4. This is K, yes. This is Q4. Yes, that's good. And then parenthesis, and then this is Q1. Q1 is indeed 6.4 E minus 19. Yes, it is. Times sine of theta 41 is sine of theta 222 with my numbers. So that, I'm feeling good about that. Times the distance between 1 and 4 is D1, and D1 is given as 0.047. 4.7 centimeters is 0.047 plus, so I got all of that, R41. Q2 does have a value of 6.4 E minus 19 times sine of theta 42, sine of 270, all over the distance between 4 and 2, which is D2. And D2 is 0.027. All right. So just being paranoid. Only the paranoid survive. All right. So let's get a number on this and put this in calculator memory location B. .99 E9. I have a number. Calculator memory location B. Store alpha B. Going to do it again. Double check. All right, I got, let's see, minus alpha B. All right, I got the same answer twice. Always a confidence builder. And specifically, my answer here is negative 6.6. No, it's negative 6.16 times 10 to the minus 24th. Even smaller. Newtons. Okay, so that's it. This is my net X component acting on particle 4. This is my net Y component acting on particle 4. You need to express those in terms of a magnitude and direction. So step 9, this is what's going on. You have, let me draw a little graph here. This is what's going on with what you've just found. okay, you have a net X force going in the negative direction. All right, here's your X force. Let me make that a little bit thicker. Okay. And then here's the net Y force. That's also a negative. Let me label these. What are these vectors? Again, this is vector A. Vector A, this is calculator memory location A, and this equals F4 net X. F4 net X. That's what this is right here. This is vector B. Vector B is the force, the net force acting on particle 4 in the Y dimension. That's what this force is right here. And again, negatives because my calculator said so. My calculator said I got a negative sign for my Y result and a negative sign for my X result. So this is the magnitude. It looks like this vector right here. This is the magnitude. This gets labeled the net force acting on particle 4. It's right there. That's it. This is the dollar sign. So this is a job for Pythagorean theorem. Just do calculator memory location A squared plus calculator memory location B squared, because that's what, let me actually back up. This is just F4 net X squared. So it's Pythagorean theorem. All I'm doing is Pythagorean theorem plus F4 net Y, Pythagorean theorem again, squared square root. So it's as easy as taking memory location A squared plus memory location B squared, square rooting it. And when I do that, alpha A squared plus alpha B squared square root, I get 1.2909, 1.29 and some change, 1.29 and some change times 10 to the minus 23rd newtons. That's the answer to part A. That's the magnitude. And now, even the problem actually says specify that angle, but specify the angle as counterclockwise direction. All right, so they want you to actually specify this angle right here. Okay, that's the angle. So for that, I guess I'll call this step 10. Step 10. Well, here's how, let's see. Theta 4 angle. All right, so I'm going to do this. I'm going to call this angle right here theta. This is theta. So I remember and this is a right angle triangle. So if you have a right angle triangle, you can use SOHCAHTOA and trig. So for this triangle that I'm working on here, I can see that, well, tangent of theta equals side opposite. SOHCAHTOA, side opposite. Side opposite is sitting there in memory location B over side adjacent. Side adjacent is sitting there in calculator memory location A. So for me, then I'm going to get theta equals inverse tangent of B over A. And I got a number. I'm going to get a number for the angle. And then I guess be done. Oh, not quite done, because that's just the angle for theta. So let's see, angle inverse tan. I'm going to do an inverse tan of alpha B divided by alpha A, and it's 28 and some change. But I'm not quite done. It's 28.534 degrees. Number 11. Aha. I'll call this angle. What's a good answer? Angle, what haven't I not? Theta net. That's good. Theta net. So I'm going to say theta net equals 180 degrees plus theta equals, I'm just going to add plus 180 or 208.53, 208.5 degrees. And we're done. What a problem. This is the answer to part B. This is the answer to part A. This is B. This was A. So quite the experience. Again, I just wanted to preempt. I wanted to preempt any suggestions to make things a lot simpler, a lot sooner. Just because now you're ready for this. You're ready for a situation where there aren't really easy simplifications or really obvious simplifications to be made. So that, let me just zoom out. Okay, zoom out one more time. Let me maybe move. I'm going to do some relocation here. It's now 11:20. Well, there goes the spreadsheet time. I'm going to just take this. Okay. I don't know if that helped. I don't think it did. Okay, so I'm just going to leave this here. That's everything. There. Maybe hard to read because it's getting kind of small. That's it. So that concludes all of today's quizzes. Those are the 5 quizzes. There's 2 more in deep dives. Homework is due on Sunday. And I think I ran through everything I wanted to run through as far as what to expect on Thursday. This is the stuff you expect on Thursday. So I covered all that. This recording will be posted as soon as possible. And that's it. So if you guys don't have anything for me, if you're good, I'm good. If there are no remaining questions or requests, I will see you guys on Thursday.
Professor, could you reopen quiz 2?
Quiz 2? I will.
Yes, thank you.
Quiz 2. All right. Done. Or I'll do that. I'll leave this screen up for a few minutes and I will open quiz 2.